All right, let's go ahead and try to use our techniques of calculus to help us sketch a graph of the rational expression x over x squared plus 1. We have a polynomial on top, a polynomial on the bottom. This is a rational function. So let's start by taking a look at the first derivative. So y prime, in this case, as we call the original function f, we can also call this f prime. We're going to use the quotient rule to take the derivative. So quotient rule, derivative of the top is 1. The bottom is x squared plus 1 minus the top, which is just x. The derivative of the bottom is 2x, all over the bottom squared. X squared plus 1, all squared. And we can do a little bit of simplification there. So if we multiply the top out, we have x squared plus 1 minus 2x squared. So x squared minus 2x squared is minus x squared. And then we have our plus 1. And the bottom is x squared plus 1 all squared. We'll resist the urge to multiply that all out. Let's discover where the first derivative is equal to 0, where it's positive, where it's negative, where it's undefined. Start by taking a look at where it's equal to 0. So we will set y prime equal to 0. A fraction is equal to 0 where the top's equal to 0. So minus x squared plus 1 is equal to 0. That's the same as x squared minus 1 is equal to 0. And that factors is x plus 1, x minus 1 equals 0. So in other words, x equals negative 1, or 1. I've left space over here to have a sign chart for the first derivative, for the second derivative, and I left space for a graph. So let's put a scale over here. We'll mark that as 0, 1, 2, negative 1, negative 2. And we can see that the first derivative is 0. At negative 1, we'll put a 0 there, and 1. Now we have our first derivative is a continuous function. We can tell it's continuous because it's a rational function, and the denominator is never 0. So we have a nice continuous function here. We can see that that y prime is never undefined. And let's go ahead and take a look at the three sections that we've divided the real line up into. The part to the left of negative 1, the part between negative 1 and 1, and the part to the right of 1, and see whether the first derivative is positive in each of those parts. I'll start with a value to the left of negative 1. I'll plug in negative 2 to the first derivative. So I will put a negative 2 wherever you see an x in the first derivative. So that would be minus negative 2 squared plus 1 all over negative 2 squared plus 1 all squared. Now on the top we end up with negative 2 squared. That is 4. With a minus in front is negative 4 plus 1 is negative 3. On the bottom we end up with negative 2 squared. That's 4 plus 1 is 5. Squared is 25. It doesn't really matter what the value is so long as we recognize that it's negative. And so the first derivative is negative to the left of the value negative 1. We can plug in a value now between negative 1 and 1. I'll plug in 0, f prime of 0. And if we plug that in, we'll see that we get the value 1 on the top, and we get the value 1 on the bottom, and that's certainly positive. And so the first derivative is positive between minus 1 and 1. And I'll plug a value into the right of 1, let's say 2. And if we do that, we'll find that we get the same value that we had up here, minus 3 over 25, which is certainly negative. And the first derivative tells us where the function is going up to the right or going down to the right. Going down to the right over here, up to the right, down to the right. So decreasing on this interval, increasing over here, decreasing again over here. Now, I didn't ask you to record that, but I'm going to go ahead and do that anyway. So f is increasing from -1 to 1, and it's decreasing on the interval -infinity through -1, and also from 1 to +infinity. So it's decreasing on those two intervals. And I also didn't ask you to record where the function had a relative extrema, but it's clear that we have a relative minimum at x equals -1, and a relative maximum at x equals 1. And I think that's about as much information as we're going to squeeze out of the first derivative. This is the first derivative over here. Let's go ahead and now we'll take the second derivative. So y double prime, or f double prime of x. This is going to be a little bit more involved algebraically. So here we have f prime in its simplified form. Let's go ahead and use the quotient rule on that. The derivative of the top is going to be minus 2x. The bottom is going to be x squared plus 1 all squared minus the top, which is minus x squared plus 1. The derivative of the bottom, we'll need the chain rule to take the derivative of the bottom. So we will have a 2, an x squared plus 1 to the first power times a 2x, all over the bottom squared. So x squared plus 1 squared, all squared, so that's the fourth power. That's a pretty forbidding looking expression. Let's go ahead and try to simplify that. We can begin by noticing that we have two terms on top, this term and this term, and each one has an x squared plus 1 in it. Let's go ahead and factor that out and see what we have left. So x squared plus 1. From this first term, we're left with a minus 2x and another x squared plus 1. From the second term, we have the minus x squared plus 1, that minus sign, and we have the 2x and the 2. So I'm going to bring this minus sign in and distribute it. So I'll write that as plus x squared minus 1. The 2 times 2x is 4x. And I'm left with the x squared plus 1 to the fourth power on the bottom. And we'll go ahead and cancel this with one of these. That's perfectly legitimate. X squared plus 1 is never 0. So we don't have to worry about inadvertent division by 0 or any such. So we have, after we do that, it makes that a 3. So I have an x squared plus 1 cubed on the bottom. On the top, I'm left with a minus 2x cubed minus 2x. And then over here, I have a plus 4x cubed minus 4x. I have my x squared plus 1 cubed still on the bottom. And once I collect up like terms, I have a 2x cubed minus 6x on the top. And that factors. I can factor a 2x out of that. So 2x, I'm left with x squared minus 3 over x squared plus 1 all cubed. Let's go ahead and take a look at that expression, figure out where it's positive, where it's negative, where it's 0. Certainly not undefined anywhere because, again, the denominator is never equal to 0. So let's set y double prime equal to 0. A fraction again is equal to 0 where the top is equal to 0, so 2x times x squared minus 3 is equal to 0. And I can factor the x squared minus 3, so 2x times x minus root 3 times x plus root 3 equals 0. So x equals 0 equals negative root 3 from that, and it equals plus root 3 from there. And let's go ahead and mark those on a sign chart for the second derivative. So f double prime. Again, I'll put a scale on here, minus 2, minus 1, 0, 1, 2. So the second derivative is 0 at x equals 0. It is equal to 0 at root 3. And it is equal to 0 at minus root 3. And now I can go ahead and plug values into the second derivative in its simplest form to figure out where the function is positive and where it's negative. I've divided the real line this time up into 1, 2, 3, 4 parts. If I plug negative 2 into f double prime, I see that I end up with 2 times negative 2 times negative 2 squared minus 3 all over negative 2 squared plus 1 all cubed. Now we could go ahead and compute this, but we can just as easily figure out its sign. 2 times negative 2 is negative. This bracket's going to be positive, so negative times positive is negative, and the bottom is certainly positive. So we have a negative divided by a positive. This is less than 0, so f double prime is negative over here. And we can go ahead and plug values into the second derivative between negative root 3 and 0. Say we plug in negative 1, we'll find that we get a positive value. Again, I should note that we don't always switch sign when we cross a place where a function is 0 or undefined, but in this case we do. If we plug 1 in, we'll find that it's negative, and if we plug in 2, we'll find that the second derivative is positive. In each of these cases, we're plugging into the second derivative, not into the original function, not into the first derivative. And so the function we see is concave down over here, concave up, concave down, concave up. So we have our function is concave up on the intervals negative root 3 to 0, and also from root 3 to plus infinity. And it's concave down on the intervals negative infinity to minus root 3, and also from 0 to plus root 3. And we have 3 genuine points of inflection where the function is differentiable and the concavity switches sign. So we have points of inflection at x equals minus root 3, at 0, and root 3. All right, let's go ahead and investigate our intercepts and asymptotes. So we take a look at our intercepts. We'll begin with the y-intercept. To get the y-intercept, we set x equal to 0, so y is equal, in the original function, so y is equal to 0 over 0 squared plus 1. That's 0, so this thing crosses the y-axis is 0. If we want to take a look at our x-intercept, we'll set y equal to 0, and so we end up with x over x squared plus 1 is equal to 0. A fraction is equal to 0 where the top equals 0, so long as the bottom doesn't equal 0 there also. So x equals 0. So this thing crosses the x and the y-axis only at x equals 0. We can see right away that the original function has absolutely no vertical asymptotes or holes in the curve. The denominator is never zero. There are no discontinuities at all. If we're looking for horizontal asymptotes, we can see that it in fact does have one. The degree of the numerator is smaller than the degree of the denominator. If we were to take a look at the limit as x goes to plus infinity or minus infinity of x all over x squared plus 1, we would find, in fact, that we get 0. You can use the old trick where you multiply the top and the bottom by 1 over x squared, and you'll find that you get 0. So we have a horizontal asymptote at height 0, no vertical asymptotes at all. Now we're just about ready to graph this thing. Let's plug in a few important points, the x-coordinates of a few important points to get the y-coordinates. So if I plug in x equals -1, I will find that y is equal to -1/2. Now again, I'm plugging into the original function, y equals x over x squared plus 1. And if I plug in x equals 1, that's an important point because we can see that we have a maximum there. I'll find that I end up with y equals 1/2. If I plug in our points of inflection, we already know that if we plug in 0, we get 0. We worked that out already. If I plug in x equals minus root 3, I'll find that y equals minus root 3 over 4. And that's approximately equal to negative 0.43. And if I plug in x is equal to root 3, I'll find that y equals root 3 over 4. That's approximately equal to 0.43. So that should be sufficient for us to make a pretty good sketch of this function. Let's go ahead and draw in a vertical asymptote, a vertical axis rather. Of course, we'll put it right beneath the 0. And here we would have, let's put x equals 1/2 there, x equals 1 is about there, so here's y equals 1/2, this is our y-axis. Here's y equals -1/2. So at x equals minus root 3, we see that the y value is equal to about minus 0.43. So let's go ahead and mark that in over here. So minus root 3 minus 0.43, so right about there. And at x equals -1, we're at -1/2. At x equals 0, we're at 0. At x equals 1, we're at 1/2. And at x equals root 3, we're at about 0.43. Now let's go ahead and complete the rest of our sketch. From negative infinity to negative root 3, we see we have a decreasing function, and the function is concave down. We know it approaches the x-axis asymptotically. So decreasing, concave down, decreasing on a hill, it's going to look something like this. Decreasing, concave down. From minus root 3 to -1, we're still decreasing, but this time concave up. So decreasing in a valley. From -1 to 0, this time we're increasing. Again, concave up, so increasing in a valley. From 0 to 1, again increasing, but this time concave down, increasing on a hill. Shaped like a hill there. From 1 to root 3, going downhill, decreasing, still on a hill, still concave down. So we'll try to draw that. Try to draw that as if it looks like a hill. And after that, we are still decreasing, this time concave up. So decreasing in a valley, we're going to approach the x-axis asymptotically. So the function is going to look something like this. And there we go.